How could it be that a particle that creates all our matter is so elusive that scientists just can't get their hands on it? Scientists recently announced a puzzling discovery at the Large Hadron Collider, and it's clear that we were wrong about the God particle. The Higgs boson was supposed to finally give us the key to the blueprint of creation, but instead, it opened the door to a previously unknown dimension of reality. At the threshold of the Higgs field, the smallest particles, which form the basic building blocks of our world, acquire the potential for mass. At this magical threshold, what was previously pure energy and pure possibility becomes visible. The physicist Peter Higgs postulated the existence of this energy field, which permeates the entire universe, as early as 1964. The particle that predominantly corresponds to this field is the Higgs boson, which researchers also jokingly refer to as the God particle. Particle physicists have been researching the Higgs boson in the Large Hadron Collider for more than a decade. Yet, the behavior of these tiny units of our creation still raises many questions today. Why do these bosons behave so unpredictably, and why do they split into many other particles immediately after their appearance, making them almost impossible for researchers to grasp? Researchers like to explain the Higgs field as an ocean of invisible substance. All known elementary particles come into contact with this field, but each reacts completely differently. Photons, or in other words, particles of light, move through the Higgs field like elegant, streamlined fish. They glide through, and when they come into contact with the field reacts at most with elegant stretches, just as a streamlined fish in water hardly causes any waves or resistance. Particles such as electrons or quarks are not quite so elegant in conjunction with the Higgs field. They behave more like an average human swimmer. We also move quite elegantly through the water, but we create a lot more waves and resistance. Overall, W and Z bosons behave in much the same way as a smooth ball would float on or in water. The ball itself doesn't actively interact with the water, but it doesn't cause much of a ripple either. The Higgs boson is the really fascinating thing about this field. It floats like waves on the surface. For scientists, this Higgs boson is the key to understanding mass conferral. It is not only a part of the field but also the actual proof of its existence. The particle was first discovered in 2012 at the Large Hadron Collider of the CERN organization in Geneva, Switzerland. The discovery of the Higgs boson proved Higgs theory from the 1960s and is considered one of the greatest scientific achievements of the 21st century. With its help, we could find out how matter is formed. Compared to other particles, the Higgs boson is extremely heavy. It has a mass of around 125 giga-electron-volts per speed of light squared, which is around 133 times heavier than a proton. The discovery of the Higgs boson was so revolutionary because it showed that the Higgs field, which had long been hypothesized, is real. The more particles interact with this field, the more mass the particles are given, and of course, the heavier they become. Interestingly, photons, which are carriers of light in the elementary particle range, do not interact with the Higgs field at all. They just slip through and thus remain massless and, of course, incredibly fast. Is matter really that volatile? The Higgs boson, which gives rise to all matter, is far from predictable. Scientists describe this unpredictability of the Higgs boson with its short lifespan. Higgs bosons only exist for around 10 to the power of minus 22 seconds before they decay into other particles. Based on these decay processes, scientists can actually gain a lot of new information about the properties of the Higgs boson. However, this particle does not make it so easy for scientists. It decays so confusingly and unpredictably that it's almost impossible to draw any meaningful conclusions from it. So, it currently looks as if we are getting further and further away from understanding what the Higgs boson's real role in the universe is. We still only know for sure that they somehow give mass to the other elementary particles, but they themselves are so fleeting that this is difficult to imagine. However, it's also certain that the world as we know it would not be possible without the Higgs boson and the Higgs field. Without the field, there would be no atoms, no molecules, no elements, no trees, and no birds. Indeed, our entire globe basically only exists because the Higgs boson gives electrons, protons, and neutrons their mass. Somewhere in the subatomic range, the decay of the Higgs boson takes place in fractions of a second. In the subatomic world, the end products observed so far are the decay into W and Z bosons, which are carriers of the weak nuclear force. However, decay into tau leptons, which are something like heavier relatives of electrons, is also possible. The decay of the Higgs boson into photons is particularly exciting. This process takes place via a complex mechanism called a loop, in which virtual particles appear and disappear temporarily. Even more puzzling is the decay into a photon and a Z boson. A recent study at the Large Hadron Collider has shown that this decay occurs about 6.6% of the time, while the standard model calculations predicted a rate of only about 0.15%. The scientists have not yet been able to derive a rule, and it almost seems as if the Higgs boson is behaving more and more erratically the closer the researchers want to get to it. Nevertheless, with every single one of their test runs, the scientists are aware that they are opening windows onto previously undiscovered particles and phenomena. These studies will one day provide us with the keys to understanding nature and the universe. First of all, the CERN scientists crisply admit these surprising new observations have to be incorporated into the existing standard model of particle physics. The deviations from theoretical predictions could be an indication of previously undiscovered aspects and forces in the subatomic world, but they could also revolutionize our understanding of matter and energy. The standard model of particle physics is also no longer the newest. Developed in the 1970s, it was a theoretical framework that describes the fundamental particles and forces that make up our universe. Particles such as quarks and leptons, as well as force transmitters such as photons and gluons, or the Higgs boson, were long pure assumptions until they were confirmed by the work in Geneva. The breakthrough celebrated in 2012 with the existence of the Higgs boson was seen as the last missing piece of the puzzle in this model. With a mass of around 125 giga-electron-volts, the Higgs boson is unique. It's also unique in its ability to give mass to other particles through the Higgs field. But can a particle that is practically impossible to grasp and describe according to the current rules really be the final piece of the puzzle? The significance of the discrepancy between observations and calculations should not be underestimated. The standard model has proven to be extraordinarily precise in countless experiments, with predictions that are accurate to fractions of a percent. Only with the Higgs boson does it fail. We may be dealing with a new fundamental force here, or we may have to prepare ourselves for the fact that researchers are still finding smaller particles and that our search in the subatomic realm is just as infinite or inscrutable as the search for the end of the universe. It's not yet entirely clear what role dark matter and dark energy play in the subatomic world. Researchers are also on the trail of these two at CERN. There have been indications that axions could be the building blocks of dark matter, but these findings have not yet been confirmed. Has the LHC opened a dimensional door? Scientists in Geneva spent years rebuilding the particle accelerator, which was not only received with approval by the public. Some critics are of the opinion that the experiments underground are dangerous, and that the enormous forces with which scientists collide particles here can tear cracks in the fabric of space-time or in the Earth's magnetic field. The Large Hadron Collider is the largest particle accelerator in the world and a masterpiece of engineering. Many nations were involved in the construction of the facility, and it's currently the best and only way to explore the world of the smallest particles. The collider accelerates protons to nearly the speed of light and causes them to collide, creating conditions that are said to be similar to those just after the Big Bang. The LHC's ATLAS and CMS detectors are highly complex devices capable of detecting and analyzing the tiny debris from these collisions. To accelerate them, scientists use the strongest magnets ever created on Earth and enormous amounts of energy. The planned high-luminosity LHC will enable an even higher collision rate, which also means even stronger magnetic fields and even more energy. Scientists expect the upgrade to result in even more precise measurements and possibly the discovery of new particles or phenomena. But is it really worth the effort, and are we possibly taking incalculable risks? Critics of the facility link strange weather phenomena in the vicinity of Geneva with the experiments in the LHC. Allegedly, a gigantic thunderstorm formed during one of the last test runs, in the middle of which a kind of strange eye could be seen. A boy from the USA, who is regarded as a clairvoyant technological genius, came forward, like the famous medium Edgar Cayce. Max Laughlin predicts amazing things about the world. Max has spoken in interviews that the experiments in Geneva would have opened a dimensional gate as early as 2022, and that we would now find ourselves in a completely new reality without realizing it. Neutrinos and muons are ghost particles, and the variety of particles that scientists have now discovered is almost unbelievable. Neutrinos are among the most fascinating and mysterious elementary particles in physics. They are extremely light, so their mass is almost zero and virtually interaction-free. This means that they simply pass through ordinary matter without influencing the matter or being influenced themselves. A neutrino can therefore truly pass through walls, which is why scientists also call neutrinos ghost particles. These particles are produced in huge quantities during nuclear processes such as those that take place in the Sun or in supernova explosions. Neutrinos occur everywhere in the universe, and every second, trillions of these particles pass every square centimeter of the Earth. Due to their very low interaction rate, they are extremely difficult to detect, and researchers travel as far as the South Pole to study neutrinos there, undisturbed. Thanks to muon tomography, archaeologists were able to completely illuminate the Great Pyramid of Giza with the help of neutrinos and discovered a completely new walled chamber in this legendary building. Another fascinating particle is the muon, which is something like the electron's heavy cousin. Muons are created in the upper atmosphere of our planet when cosmic rays collide with atoms. Muons are extremely unstable and decay into electrons and neutrinos within microseconds. Like the Higgs boson, muons exhibit anomalies that are not consistent with the standard model of particle physics. In particular, the magnetic interaction behavior of muons appears to be stronger than theoretically predicted. Researchers suspect that muons could also show us the way to completely new areas of physics and natural science.